My name is Sailaja, and this is Brian. We both work with Enterprise Cloud Computing, which is a business unit within Fidelity Investments. We spearhead the organization's journey to the cloud. Just a quick disclaimer there. And let's get started. What is chaos engineering? Chaos engineering is the process of deliberately introducing faults into your systems, into your infrastructure or our applications, just so that you can find the weaknesses within your system to make it more resilient and away from failure. So when I say infrastructure, it can be your instances, your load balancers, your availability zones, or even regions. So we already have a lot of levels of testing. You have unit testing, integration, acceptance. Why do we need to add one more layer of testing? So there's basically two reasons. One is that we can now, and the other is we kind of have to. So this quote aptly captures what happens to a system that's running now. You know, everything is going to fail at some point. It's not a question of if it's going to fail, it's just when. So chaos engineering, especially in the world of microservices, you have a lot of systems talking to each other. You have services within your organization talking to internal services, externals, to databases, to queues. And with a lot of systems in communication, you have a lot of opportunities for failures to arise. And you want to be on top of them. You want to know them before your customers find out for you. And I can't imagine doing chaos testing maybe a few years ago or even a decade ago. You know, you have one server that's one monolithic service running, and it's quietly humming away in some part of your office, in your data center, and probably the only way to chaos testing there would be to start plugging out wires or start smashing things. But now you have the opportunity to control each and every part of your infrastructure. You have APIs to do everything. You want to stop an instance, you have an API. You can introduce latency. You have complete control over your infrastructure. And with recent developments, you can also inject failures into your application. It's still in its infancy. Some providers do it, but the infrastructure part is really covered. You have complete freedom over there. So how do you even get started with chaos testing? What are the basic principles of it? So the first thing is defining a steady state. When I say steady state, what is it? It is the normal working state of your application. So we can measure it in a few different levels. So if you're a basic application, you have one developer, you have one application. It's some web application that's serving content to your customers, right? So the one way to test it would be to go into your browser, see if everything is logged in. You have the content. Is that perfect? So that's one way to get the normal working state of your application. So you have next level is you have many more applications. You go on to the next level. This manually checking business doesn't work there. So you kind of have to have metrics on your systems. So you have some things like the system metrics. You have CPU usage, you have latency, and other stuff that you measure using open source tools or using commercial tools. But this lets you define the steady state of your system. And then we can also go one more level. You have business metrics. These are very specific to your organization. These are very specific to the area that you're in. So this forms like a combination of system metrics with your business metrics. So an example, say, let's take a big e-commerce provider. So your business metrics can be defined as something like number of transactions per second on a given average day, or number of signups, the amount of revenue that you generate. That can be a business metric. So we have all these metrics. What do we need them? So the whole point of chaos engineering is you define these metrics, you know the steady state of your system, and then you inject kind of experiments, faults into your system, and see how these things affect your steady state. So that leads us to the next part, creating a hypothesis. To create a hypothesis, you need to know the basic steady state of your system, and then you make an assertion. Okay, if I do this, something's going to happen. It can be positive, it can be negative. You might not even know what's going to happen. That's another way of chaos testing. But in basic, you have an assertion of a hypothesis. A basic example would be, if I turn this instance off, the application is going to go down. That's a very valid, crude hypothesis. But you can also have something as complex as, if the whole region goes down, I have DR scenario where it switches on to another region, and I have the application running within 3 seconds. So that's another complex hypothesis. But no matter what, you need to have some sort of hypothesis before you do chaos testing. So the next one is to simulate real event. You have your steady state, you have your hypothesis, but you're not going to start testing, especially when you're starting out, you're not going to start testing on your production system. Maybe you'll start on your lower environment, your production-like systems. But then you know about the problems of testing. You know, the data is never the same as your production in any of the lower environments. So the whole point of chaos testing is to simulate as much as close as possible to your production system, so that when you introduce an experiment, it affects the lower environment as much as it'll affect the production environment, so that you can get some insights onto your system. So you can do that. Taking the same example, e-commerce provider, you have 10,000 transactions per second in that given hour. In your production system, you use some sort of load generating tool to do the same amount of load in your lower environment where you're testing it. So yeah, so we have all the experiments done. It's all done. We have the steady state hypothesis, we have generated load, and you're starting the experiment, and something goes really wrong, and it goes haywire. The whole experiment goes haywire, and your production system gets affected, and your customers get affected. That's the last thing you want with a chaos experiment. The name sounds scary, it's about chaos and everything, but the last thing you want is a chaos happening in a chaos experiment. So chaos experiment is really controlled. It is precise. So you have to take all the steps to minimize blast radius. There are a few different strategies on how we do that. I can give you a few examples. You can start testing on a time where there's least amount of customers, or you can do some sort of canary analysis where you only direct one part of traffic to the chaos experiment, and you do the other part just go normally. And there's also a few organizational principles here. So say you're testing your Kubernetes cluster, and you want to make sure that the team who's responsible for maintaining the cluster be on call, or at least are available to do a backup. And also, maybe if you have some services that depend on your service that you're testing, you might want to let the other organizations within your internal organization, you can let them know that you're doing a testing, you've taken the necessary precautions, but just that you're running a chaos experiment. These are all just precautions that you take to minimize the blast radius. So I'm just going to walk through the flow of creating an experiment and running it. So this is going to be very similar to what I've talked, but this is in a more streamlined flow. So first thing is to pick a hypothesis, the steady state hypothesis, and then you choose the scope of the experiment. Your hypothesis and the steady state determines what the scope of the experiment is. You know how far you want to push the system in. And the third part is identify the metrics. This is key. So there's two forms of chaos testing. You can do exploratory testing. Okay, I'll do this and see what is going to happen, but you get more value out of your chaos experiments if you know what you're exactly looking for. So defining the steady state, okay, you have 75% CPU usage for normal state, and then you use the experiment, and then you're going to watch that, identify the metrics that you're going to watch that as the experiment runs on. And then for the same thing that I've talked about earlier, notify the organization, let your peers know, and just that. This is only during the basic level. When Brian's going to talk a little bit about the levels of chaos testing, once how it goes into your organization. Maybe during the advanced level, you don't even need to do this because people are aware that it's part of the culture that chaos experiments happen on time. Our software architecture is architected in such a manner that it can handle those failures. So now it's the time to run the experiment. So it can be automated, it can be manual, but you run the experiments and then you analyze the results. This is looking at the metrics and see how they differ. So based on the results, you have one or two things. The first one is the hypothesis failed or the hypothesis passed. A failed hypothesis is not a bad one. Actually, it's a really good one, meaning you have identify some weakness in your system that would have gone to production if it wasn't for the experiment. So, and then if it passed, you can further push your system to build up more confidence in your system, increase the scope, and then you can also codify the whole experiment as code, and you can use your CI systems to run this every so often so that you have continued confidence in your system. So I wanted to do a live demo, but just due to time constraints, I'm going to just show you some of the one of the experiments that we ran. It's a very simple, basic experiment just to let you understand the basic structure of a chaos experiment. So as you can see, it's just one EC2 instance sitting there. It's a Flask application. It's serving a web service. And then you have the mouse is not here. So the chaos toolkit, that's the toolkit we use. It's written in Python. It's open source. You don't have to necessarily use this. There are commercial options as well. You can choose whatever you want. We just chose that because it was written in Python. It's open source. And then it uses AWS, like the Boto libraries to control your infrastructure. So with this, you have the option to turn off an instance, do a lot of other stuff. There's one plugin which lets you inject latency into your application as well. But we're not doing anything fancy here. We're just turning off that one instance and see. That's our experiment. So this is a JSON that the Chaos Toolkit accepts. So on the top, you can see the metadata, so it lets you version your file, lets you, in basic English, what is the application, what is the experiment all about, what is your assertion. And then you go to the steady state hypothesis. The steady state hypothesis is the application response, no matter what you do to it. Is it going to fail? Is it going to pass? It depends, but we know there's one instance, and if you do something to it, it's going to fail, right? So. And it just checks the URL, and the tolerance is 200. So it accepts 200 as the only tolerance value. And then you have the method. This is the actual experiment that we are going to run. So it stops an EC2 instance. So it just kills the specific instance ID within your AWS and then waits 10 seconds after. So the way how Chaos Toolkit runs its experiments is, so I hit run, and then it checks the steady state hypothesis first, see if the application is up, and then it does the action. So that's the stopping the EC2 instance, and then it checks the steady state again, where you see there. And then obviously we know it's going to fail because there's one instance, and if we kill the instance, it's gone. And then that's how you identify the weakness. And then you can say, put a load balancer there, put an extra instance there, and then maybe check there, and then your experiment passes. That's how you work around that. But this is about the basic structure of a chaos experiment, the principles. But how do you bring this into your organization? So there's a cultural shift that's needed within an organization, especially when you're starting. What is the value? How do you tell the people about the value? How do you grow it? So I'll have my colleague Brian talk about that.
So I'm here to talk to you all today about the chaos maturity model. So the chaos maturity model, it's broken down into two separate pieces. The first is the adoption, and then the second is sophistication. So firstly, I'm going to talk about sophistication. What does sophistication mean? Well, sophistication, it kind of looks at the level of your experiments, what kind of experiments you're running them, where are you running them, what are you doing with the results. And we've broken the sophistication down into 4 separate levels, all the way from elementary up to the advanced level. So what does each one of these mean? Well, let's start from the bottom. So elementary. The elementary level, you're running your experiments in non-production. Typically, everything is done manually. So from the setup of your experiment, the execution, the analysis, and the termination of your experiment, if it need be. And it's looking at just system metrics, so things like, as Vel mentioned, CPU, latency, memory. And they're very, very basic events. It's this concept of shut it down, turn it off, plug it out if you can get to the cable. So these might seem quite basic experiments, and they are, but what elementary experiments do is they give you a feel for chaos testing, so defining your steady state, coming up with the hypotheses, what does running an experiment look like, how do we analyze the results, and how do we terminate it. So the experiment that Vel showed is definitely an elementary experiment. So as we move on from elementary, we go to the simple level. And again, simple is it's non-production, but this time you have some traffic in your system. So this traffic could be generated with a load tool. There's many options out there. Or you could run in a user acceptance or staging environment where you have users testing out potential features you want to push to production. And now we've started introducing levels of automation into our experiments. So in this case, the execution of the experiment is automated. And while the execution is automated, everything else is still manual. So you monitor the experiments manually, you terminate your experiments manually, and you analyze your experiments manually. And we've moved away from the basic events, so we've moved away from the turn it off to introducing latency, introducing CPU into our systems and see how it handles that. And then we go to the sophisticated level. So now you're running things in production. And we've increased the levels of automation another level. So the analysis and the termination of your experiments are automated. And this is really, really important. The last thing you want is to be running an experiment in production and leaving the decision down to a person. Should I shut this down? Is this affecting users if things start to go wrong? And we've started to group experiments now. So the previous 2 levels, if you think of microservices architecture, they would be kind of at an individual service, whereas this, we're now grouping experiments, so we look at the product as a whole. So if I have a product that is made up of many different microservices, grouping the experiments mean I might inject latency into microservice A, I might shut down the database that microservice C depends on and inject some latency into microservice D. And this gives you a great insight into how your system deals with multiple failures or issues in your components. And finally, we have the advanced phase. And again, you're running in production here. And we have full SDLC automation. So our automation has increased that a little bit more. What do I mean by this? So not only are you running automatically in production, but you're running through each of the different life cycles of your lower environments. So you might deploy to a UAT environment, kick off an experiment, and shut it down. And what this enables you to do is you can compare this experiment run to previous experiment runs that have ran in those environments. And if there's a big deviation in the results, you might choose not to promote that code to your higher environments before you investigate why is that the case. And here we've moved on a level from the business metrics. So previously business metrics we were looking at, can users still log in? Can they make a purchase on our system? To now we're looking at revenue loss projection. And what that means is if users are affected, if they can't log in, if they can't make a purchase, it's not just that we know they can't, it's how much is that costing us as a company. And we move on to A/B testing. So Vel mentioned one of the principles was around minimizing blast radius. So this can be done through A/B testing, canary deployments. So what this enables you to do is if there is a problem, with the experiment going on. It's only a subset of your users that are affected by that problem. And you can also do really cool things with A/B testing, like you can compare the experimental group, which is the group you're running the chaos experiment on, to the normal group, your normal users that are not subjected to any chaos. So you're probably thinking, this is all great, but how do we get there, or where do we even start? Are we even ready to do some chaos? So there's a couple of things that we think are important. There's probably many, many more, but let's just talk through them. So first of all, engineering practices. You really need a strong foundation in engineering practices. So what we mean by that is you need reasonably good levels of automation. You need a good SDLC process in place. I mean, if you're working as part of a team that's looking to increase code coverage, for example, in your services, that's perfectly fine. Maybe chaos engineering isn't for you right now. You're probably better off focusing your engineering efforts in those areas before you move on to chaos engineering. And then we have monitoring and alerting. So let's just take the experiment that Vel showed you screenshots of earlier. It's a basic experiment. So we have another experiment that might inject some CPU spikes into one of our systems. How do we know that that experiment is doing what it says on the tin? So how do we know that our system has an actual CPU spike? Well, we don't know, right, unless we have monitoring in place. And then alerting. So I'm sure many of you have had the pleasure of being on call with previous companies or your current companies, and you get alerts and you start panicking, and then you log on to your computer and you check the system and everything looks okay, so the alerts aren't been accurate. And what happens there is it starts creating this noise. The alerts start creating noise, and then you start to ignore the alerts. You say, well, I logged on last time, everything was okay, so I'm not going to log on this time. So chaos engineering really helps you answer the question, are we alerting on the right things? And I think as you start to do your chaos experiments, you will notice that when things start to go wrong, or you're manually checking the UI and I can't check out, you'll start to ask yourself the question, well, our monitoring didn't pick up on this. Why weren't we alerted on this? You want to know about the problem before your customers do. And then we move on to these three, SLOs, SLIs, and SLAs. I'm not sure how many of you are familiar in the room with these, but they are service level objectives, service level indicators, and service level agreements. So service level agreements are typically agreements between you and your customers, while SLOs are kind of your team agreements where you want to get to, and SLIs are how you measure it. So I'll talk you through an example. So if I have a product or I'm selling a service to customers, I might have an SLA with them that 99% of requests will be served under 5 milliseconds. The team that's developing the service and releasing it would have an SLO that 99.99% of requests will be served under 5 milliseconds. And the SLI in that is latency, how you measure it. So these are really important because when it comes to running your experiments and if things start to go wrong, so you're running an experiment and you have a CPU, you're looking at your CPU and it spikes at 90%, 99%. Do you really care if it's not affecting your customers? They're not seeing any issues, that's okay. However, if you're running the same experiment and your SLA, let's use the same example, your latency, before you ran the experiment, it was at 3.5 milliseconds per request, and during your experiment it starts to go to 4.5, 4.7, so now you're getting near the threshold where your customers are going to notice. That's when you really want to terminate your experiments. And not only are these, you need them as a foundation, they also help you move through the levels. So let's just pick one example around monitoring and alerting. So in the very basic, the elementary level, we were monitoring system metrics. So that's fine, that's perfect. As a team, we might have good monitoring on system metrics. To move through the more sophisticated and advanced levels, you need to have monitoring on business metrics. So maybe we don't have that in place yet. So we need to work on our monitoring to get those in place so we can monitor. And then just engineering practices as you move through the levels. I've mentioned automation many times, and that fits into your engineering practices. So how do we take this practice of chaos and adopt it across our organization? So this is where the adoption phase comes in. Again, we've broken it down into 4 different levels. So I'm just going to talk you through each one of these now. So in the shadows really means that your company isn't really aware of the concept of chaos engineering, how to do it, what it is, the benefits of it. And the only really way of getting out of the shadows is by raising awareness. So you could start that straight away Monday morning when you go into the office and say, oh, hey, I was at a PyCon conference at the weekend and there was this brilliant presentation. If it was crap, don't talk about it, but brilliant presentation around chaos engineering. And hopefully that will get people engaged and say, oh, well, what is chaos engineering? And once you have that awareness, hopefully you get investment. And what investment means is that there are multiple teams interested and engaged around the whole topic of chaos engineering. You might even have people dedicated part-time. And what this will allow you to do is run game days. So what are game days? Game days are essentially doing what Vel talked you through with a group of people or teams. So you do everything from coming up with your experiments, running them, monitoring them, analyzing them, and terminating them. So what game days do is they allow people to really see the value of chaos. So I mentioned monitoring and alerting. So if a team does a game day, they might say, oh, well, we're actually not monitoring this, or we need to alert off this now. They really help people see the value. And once you have that value or the initial investment with people, how do you scale that across your organization? So this really core group of people are interested. How do you bring that to the mass? So there's a couple of ideas here. The first one is around a community of practice or a chapter. So what that is it's a group of people, and that group of people is made up of individuals from many different business units or areas within your business. And the more areas, the better. And they could meet on a weekly basis or a monthly basis and just discuss chaos, discuss best practices, how each of those different areas are getting on. And the idea is they could take the ideas that came up here or brought up in the community and spread them down to their individual teams. You could also have a dedicated team. So the dedicated team could be used to seed in your other teams to help them bring up to speed on the whole chaos engineering, get them into the thinking behind it and how to do it. And this is also where leaderboards can come into play as well. Leaderboards, they're not meant to be seen as a competition. What they can do though is they can highlight who needs help on their chaos journey within your organization. So you would choose to seed the different members from those dedicated teams into the ones at the lower leaderboards. And it is important to note, not everyone is ready to start chaos at the one time. Each team has their own journey. So finally, once you've scaled, hopefully it becomes the cultural expectation. And what I mean by that, all services or majority of services are performing chaos engineering. It's part of the onboarding process. When an engineer joins your company, they hear chaos from day one. They hear chaos in the same breath as unit testing, integration testing. And you're in by default. So if you write a new service, you're doing chaos on that service unless you have a very good reason not to. And just to bring it all together, this is the sophistication and the adoption. So the idea is as a company, you want to get as high up the sophistication pyramid as you possibly can and as far right across the adoption pyramid. And it's important to note that when I say get up on the pyramid, not every team in your organization is going to be at the advanced level. You might have teams at advanced and teams at elementary, but at least get them on the pyramid. And the more teams you can get on the pyramid and the further across the arrow you can go, the greater confidence you will have in your system's resiliency. So that's it, just to finish with a couple of references for anyone that's interested. There's a really good book on chaos engineering. I'd recommend you to read it if you're interested. And I'd just like to thank you all very much for listening. I hope you got something out of it. I know we're up on time, so there's a coffee break now, so we're happy to talk in more detail at that. And just thanks, everyone.